Welcome again. Today we look at the spectroscopic identification of organic compounds, as we focus first on the index of hydrogen deficiency, and then the mass spectral data, then the use of infrared spectral data, and finally the use of hydrogen-1 NMR spectroscopic data to figure out or to elucidate the structure of a complex organic molecule. Let's begin first with the IHD, the index of hydrogen deficiency. When you are given the molecular formula of an organic compound like this one, C4H8O2, then you can determine the amount of unsaturation in this molecule by plugging into this formula. 2C can be found by multiplying the number of carbon atoms by 2, adding 2, minusing for the number of hydrogens, minusing for the number of halogen atoms, X, if there are any, but there are no halogen atoms here, and then adding for the number of nitrogens, and again we can see that there are no nitrogens here. Oxygen is not included in the formula. When you plug in all of these numbers into this equation, IHD comes to 1. What this means is that C4H8O2, our molecule, can have any of these structures, because an IHD of 1 means that one double bond must be present. Or it can mean that a ring structure must be present. An IHD of 2 would mean 2 double bonds, or a ring with a double bond inside of it, or even a triple bond. The index of hydrogen deficiency is the first and the most simple step towards determining the full structure of an unknown organic compound. Next, we will consider infrared spectroscopy. To put it simply, if you have a bond like a carbon to oxygen bond, here in this carboxylic acid, ethanoic acid, then at certain wavelengths of infrared radiation, the bond between the carbon and the oxygen can be likened to a spring that bobs back and forth when it's given just the right amount of vibration or the right frequency. It would begin to resonate. And it is this very principle of resonance that is used in infrared spectroscopy. Infrared radiation causes the bonds of certain organic functional groups to vibrate at certain characteristic wavelengths. So once the infrared radiation goes through the sample, then you would have transmittance, and then at certain specific wavelengths you would have absorption. And the amount of this absorption and where it occurs on this scale can be used to get some idea as to the identity of possible functional groups in the unknown organic molecule. Another source of useful data to help identify the organic molecule is mass spectrometry. And again, to put it as simply as possible, the sample to be analyzed is vaporized and ionized to produce charged particles, which go through a magnetic field, and then they are bent in accordance with mass to charge ratio. For an example like ethanoic acid, 2 fragments that could be produced would be one, the CH3 fragment with a positive charge, forming this ion, which would have a mass of 15, goes through and gets detected and gives a readout of 15. 15 is typical of the fact that a methyl group is present in the structure. The 60 here is present from an ion that is produced by this ethanoic acid molecule simply losing an electron to form this with a positive charge, and to give you a value of 60. In the IB exam, students are only required to identify a limited number of groups, and the groups that you're expected to identify are the ones provided in the data booklet. The one thing that would not appear in the data booklet would be this peak of 60, which corresponds to the full molecular mass of ethanoic acid. All of the other peaks that you would be expected to identify would correspond to groups like methyl groups and all the groups presented in the data booklet. And finally, we consider hydrogen 1, nuclear magnetic resonance. And again, we take a very simplistic look at the technique involved. Hydrogen 1 consists of a single proton. When this hydrogen 1 is part of a bigger organic molecule and it is placed inside of a magnetic field, the protons can either align with or against this magnetic field. Some of the protons align with the field and some of the protons align against the field. This leads to a splitting, and in the NMR machine, radio waves also get sent through the sample. When the energy of the split coincides with the energy of the radio waves, then resonance occurs and the particles begin to move up and down within their energy levels. This value of the split provides information about the nature of the hydrogen's environment. For example, these hydrogens here in this structure, C5H12, tetramethyl silane, they are all in what we would term a chemically equivalent environment. So the hydrogen NMR spectrum for TMS would reflect that 12 hydrogens exist, and they all exist in the similar chemical environment, or they're all chemically equivalent, because the magnetic field and its effect on the protons behaves differently based on how closely the electrons are associated with each hydrogen. All of these hydrogens are attached to carbons by single bonds, and they are said to be chemically equivalent. When this TMS is placed into the NMR device, it gives a value which is used as the baseline for all other readings for hydrogens on other structures. TMS is particularly useful for this purpose because when it's introduced into the sample, its volatile nature allows it to be easily evaporated and separated from the sample afterwards. So let's look at this ethanoic acid molecule, and if it were put into the NMR machine, then the data generated from each of the hydrogens in this structure would be compared relative to the TMS value, which is the baseline, and given a value of 0. The extent of this difference is quantified and known as a chemical shift, measured in the unit of parts per million. For this particular case, these 3 hydrogens are in what is termed a chemically equivalent environment. And when influenced by the magnetic field and splits are created, all of these 3 hydrogens would have the same split, and the same wavelength of radiation would be required to cause them to resonate. So these 3 would account for 1 chemical shift. This hydrogen here, which is in a completely different environment, in fact it's in one which is highly de-shielded, attached to the electronegative oxygen and then to this pi bonding system here with this oxygen. Electrons are pulled over on this side, and this hydrogen is highly de-shielded, meaning that it's making it get influenced by the magnetic field in a completely different way from these hydrogens. And the chemical shift in this case is even more downfield of the standard molecule TMS, having this value here of 1. When an integration trace is provided, or a low resolution nuclear magnetic resonance spectrum is provided, it's important to not try to compare the length of these lines to determine the number of hydrogens, but you would need to look at a number that might be provided, like a 3 or a 1, 3 representing this and 1 representing that, or to look at the length of this line compared to the length of this line, this being termed the integration trace. And here you can see that this is 3:1. And what this means is that you have a methyl group, and you know that because it means 3 equivalent hydrogens, and the actual value here can be looked up in the data booklet to determine what chemical shift corresponds to this group. Similarly, with this chemical shift value, you go to the data booklet and it would suggest that it belongs to the carboxylic acid group or a similar group. Each piece of data that you get is not completely definitive, for molecules tend to be quite similar. But when you add up all of the data that you can get from the IHD, infrared spectroscopy, mass spectroscopy, and nuclear magnetic resonance spectroscopy, then it is possible to elucidate or to figure out the full structural formula of an organic molecule. Students of higher level chemistry would have an additional tool available to them, or they would be considering the high resolution NMR spectrum, and this provides even more details about the structure of a complicated organic molecule. But this is the subject of our next lesson.